in solving exponential equations using logarithms. We do this because it's not possible for both sides of the equations to derive the same base, like what you see on the screen. So the first thing to do is to isolate the x term or n term, whatever variable is in your equation. And then after that, you take the natural logarithm of both sides. I'm using natural logarithm, but you can also use common logarithm. Apply the power rule, which is this, and put that exponent somewhere there, all right? And then solve x. Okay, let's solve number 1. 2 raised to x is equal to 240. So as you can see, we cannot derive uh, the same base for both sides of the equation. This is base 2, but we're not sure what real value can be a base of 240. So we can only apply a logarithm in this matter. So x is already isolated, so we can proceed to the next step, which is taking the natural logarithm of both sides of the equation. And then after that, we will apply the power rule. So power rule says that this exponent will be in the front later. So that's x ln 2 is equal to ln 240. And of course, the last step is to solve x using the properties of equations. So since we want to isolate x here, we need to get rid of ln 2. So that will be divided by ln 2. Okay, so this is the exact value that we're looking for. But of course, if you're trying to find the approximated value, meaning in decimal, all you need to do is to put this in the calculator, and that's ln functions. You can find in the miscellaneous, that's ln 240 divided by ln 2. You can also write it, it doesn't matter. So that's 0.7907. So that's the value of x that we're looking for in this equation. Now we will go to the second equation. And so you have 5 times 18 raised to 6x is equal to 26. So we want to isolate first the x term. So this is the x term here. So we need to get rid of 5 by dividing it on both sides of the equation. So making the equation 18 raised to 6x is equal to 26 over 5. Now we can apply the natural logarithm on both sides of the equation. So this becomes ln 18 raised to 6x equals 26 over 5. Natural logarithm. Alright, so we can apply the power rule now. That be 6x ln 18 is equal to, we can even put this in expanded form, okay, and that would be ln 26 minus ln 5, because when you're dividing, you will be subtracting. We're doing this because we want to obtain the exact value of our x. Now we have to isolate x, and so we need to divide both sides of the equation by 6 ln 18. And so therefore x is ln 26 minus ln 5 over 6 ln 18. Now this is the exact value again, and then of course we can always find the approximated value. This time let's use a calculator. We do alpha y equals, okay, and then enter. And of course you will type, this is ln, this is base e, natural logarithm, ln 26 minus ln 25, ln 5, divided by 6 ln 18. 6 ln 18. And that's the answer. That's the approximation, 0.095. Alright, now let's proceed to the next one. I am emphasizing E because in higher maths, E is always being used as the value that will maximize your rate over a long period of time in a compound interest. So you have here 3.4 e raised to 2n minus 9 is equal to negative 4. So our first step is to isolate the n term. So we need to add 9 on both sides of the equation. So that's 3.4 e raised to 2 minus 2n is equal to 5. Okay? So the n term is still not isolated. There's still 3.4 here. So we will divide both sides of the equation by 3.4. And so you have e 2 minus 2n equals 5 over 3.4. Now we can apply the natural logarithm of both sides of the equation. So that's ln e raised to 2 minus 2n equals ln 5 over 3.4. Again, we can always expand whenever we have a fraction by means of subtraction. Now we will apply the power rule first. And you have 2 minus 2n. Make sure you enclose it in parentheses. Okay, because you have more than one term. Otherwise, if there's no parentheses, you will be thinking that it's only 2n that's going to be multiplied by ln e equals, let's expand this, ln 5 minus ln 3.4, since we are dividing and we wanted to find the exact value of our function. Now, ln e is supposed to be equivalent to 1. So how do we find ln e using our calculator? It's going to be ln and then second ln again, because that's where you find the value of e. And then it asks you the exponent, it's 1 because you don't see it, it's 1 in algebra, and the value is equivalent to 1. In any case, if I'm going to change this into an exponential form, it's going to be e raised to 1, okay? It's also equal to e raised to 1. So that's equivalent of ln e. So just remember that it's just equivalent to 1, so you can easily cancel it. So you have 2 minus 2n equals ln 5 minus ln 3.4. And so we can now we can now subtract 2 on both sides of the equation. And that's going to make this negative 2n is equal to ln 5 minus ln 3.4 minus 2. Okay, again, my aim is to find the exact value of my n. So I'm going to divide both sides of the equation by negative 2. So n now is equivalent to, I wouldn't like my denominator to be negative. So I'm going to multiply each of these by negative 1. So this now becomes negative ln 5 plus ln 3.4 plus 2 all over 2. So this is the exact value. If you would like to find the approximate value, all you have to do is to use calculator to find it. Okay, and the last one. Okay, so you have 12 raised to 12 raised to x over 25 is equal to 1 over 32. Okay, so we need to isolate 12 raised to x. So we are going to multiply by 25 on both sides of the equation. Alright, and so you will have now 12 raised to x is equal to 25 over 32. Again, our aim is always to getting the exact value before we get the approximate value. So what we should do here is to take the ln of both sides of the equation. And so after that, we will apply simultaneously the power rule and the quotient rule for logarithm. So this is x ln 12 is equal to ln 25 minus ln 32. And so of course, we can isolate now x by dividing both sides of the equation by ln 12. So this gives us the exact value, and just find the value in the calculator to find its approximate value. And so in summary, first is you isolate your x term, n term for whatever variable you have, and then take the natural logarithm of both sides of the equation, apply the power rule. And of course, we would like to find the exact value by continually applying algebraic strategies and properties of logarithms to solve for x.